Welcome to Spring LIB.
Okay, this problem is asking us to synthesize the molecule on my right from the molecule on my left, and it has given us the hint that we should be using acetoacetic ester at some point. Okay, so let's go ahead and analyze these two. So I can easily distinguish my cyclohexanes in each of these because I have my cyclohexane here, and then I have my cyclohexane here. Okay, I also have my 2 carbons attached to that cyclohexane on my reactant, and in my product, those 2 carbons are most likely going to be these 2 carbons right here. Okay, and then that is going to be attached to this molecule on the right side of my squiggly line. Okay, so I see that I have a carbonyl, and I see that I have 1, 2, 3, 4, 5 carbons. Okay, so let's go ahead and analyze that. Okay, and I'm actually going to go ahead and draw out my acetoacetic ester, just so we know that we're going to be using that at some point. Okay, so acetoacetic ester is going to look like this. I'm going to have my ketone, and I'm also going to have that ester on the same molecule. Okay, so we're going to be combining this molecule with this molecule. It's just a matter of when, how, and why. Okay, so first off, let's go ahead and fix up this molecule. Okay, so knowing that we're going to have to utilize the acetoacetic ester, I know that this carbon is particularly, it has an acidic hydrogen, right? It's the alpha carbon, it has alpha hydrogens, it's also sandwiched between these 2 carbonyls, it's just going to be very acidic. So I know that connected to that carbon, this carbon right here, that carbon is going to be the same thing as this carbon right here. Okay, and I know that because right here I have my carbonyl, and that carbonyl is going to correspond to this carbonyl, not this carbonyl, and I know that because I have the presence of this ethoxide right here. It's going to be this one because I have the presence of the methyl group right there. So this methyl group right there corresponds to the methyl group right there. Okay, so that's kind of a lot to handle, but let's go ahead and clean that up and backtrack a little bit, because I know that I'm going to have to deprotonate this hydrogen with a base. Okay, I can deprotonate that hydrogen so that I can attach something, aka this carbon, onto this nucleophilic site, which is going to correspond to this nucleophilic site after deprotonation. Okay, so if that's a little bit confusing, I'll just do it one step at a time so we can see it all pretty clearly. Okay, so again, I need to attach this carbon compound onto this nucleophilic site if that were deprotonated. So I can't just attach this molecule straight away to that nucleophilic site simply because I have an alcohol here. Alcohols are terrible leaving groups, and I want to make that into a better leaving group so that I can more easily attach this alkyl, potentially halide, onto this nucleophilic site. Okay, so one way I'm going to do that is by transforming this primary alcohol into a primary alkyl bromide or primary alkyl halide. Okay, so one way to do that is using PBr3 and in the presence of pyridine. Okay, those are the typical reagents to transform an alcohol into a bromine. So it's going to look like this. I'm going to have a 6-membered ring still, my 1,2 carbons connected to my bromine. Okay, it just replaces my alcohol with a bromine. Okay, so now this is a primary alkyl bromide that can more easily react in an SN2 reaction as an electrophile. Okay, and then separately, I'm going to react this acetoacetic ester with a base, such as sodium ethoxide. Okay, that base is going to take off this acidic proton. Okay, and then after it takes off that acidic proton, I'm going to be left with this compound, in which I have my set of lone pairs on that central carbon, that alpha carbon. Okay, so again, that alpha carbon that we just deprotonated right here, that's going to correspond to this alpha carbon right there, which we want to connect to that carbon right there, which is going to correspond to this carbon right there. Okay, so again, it might be a lot to handle, but maybe it will make sense if I draw this actual reaction. So these lone pairs are going to behave as a nucleophile to attack this carbon. Okay, as it attacks that carbon, I'm going to have to move the electrons up to this bromine as a leaving group, so that will leave, and I'll form my alkyl chain. So the product of that will be as follows. I'll have my ketone, my ester, like that, and then attached to this carbon, we have a substituent, and that substituent is going to be my 2 carbons connected to my cyclohexane. Just like that. Okay, so the question is, are we done? And the answer is no, we're not done, because as we can see, I'll do this part in green. As we can see, we formed this part of my molecule so far. Right, we had that methyl ketone right here. That methyl ketone corresponds to that methyl part of my ketone, and we also had the connection to this chain all right here. Okay, and as we can see in my final product, we have to have, oh, and by the way, this part that I circled in green corresponds to this part in green over here. Okay, so as we can see in this final product, we still have to have these 2 carbons. Okay, so are those 2 carbons the same thing as this carbon and this carbon? The answer is just no, right? Because we have to get rid of this group entirely, and that is going to be performed in a decarboxylation reaction. Okay, so a decarboxylation is going to involve the hydrolysis of that ester into a carboxylic acid, and then after that, we can go ahead and turn that into CO2. Okay, but again, we don't want to have that occur yet because we still have to add a 2-carbon chain to this carbon. Okay, and by turning this into CO2 first, we're going to just have that blank carbon, right? It's not going to be considered nucleophilic. So we need to make it nucleophilic by deprotonating the extra hydrogen right here with ethoxide. So using ethoxide, I'm going to deprotonate that hydrogen, moving the electrons onto that carbon, resulting in that nucleophilic carbon. So same exact molecule, 2 carbons connected to my cyclohexane with my ester over here. But again, we're going to have these lone pairs over here. Those are going to behave as nucleophiles. And again, we want to add 2 more carbons. And we have to add those 2 carbons first before decarboxylation so that we can have that nucleophilic site, that specific nucleophilic site, not this site, this site. Okay, so I'm going to have the connection to my 2 carbons connected to a bromine, in which this nucleophile attacks that carbon to result in an SN2 reaction, which is going to add 2 carbons to that chain. Okay, so I should end up with this as my next product. My 2 carbons connected to my cyclohexane. Okay, and then I have that 2 carbons over here, and then last but not least is my ester, which I can now undergo my decarboxylation reaction, which is going to utilize HCl, water, and heat. Okay, what that does is turn this into a carboxylic acid, which is going to undergo decarboxylation to turn into CO2, which is eventually going to form my final product of this. Okay, so I'm actually going to draw the molecule in the way that I represented it throughout this reaction, but that reaction is going to end up being this product right here. So these two are going to be the same as this.